Eliminating the parameter is another way that we can try to be able to graph and get an idea of what the graphs of parametric equations look like. And eliminating the parameter basically means solving one of the equations for the parameter and then substituting it back into the other equation. Now, usually it's easiest to solve for x or solve t in terms of x and then substitute it back into y so we can see if we can get a function. But there are other ways that we're going to see that we can use algebraically to be able to eliminate the parameter. So what we're going to do is we're going to convert each parametric to a Cartesian, and then we're going to graph the curve and indicate the orientation as the parameter increases. All right, so we have this x equals t, y equals t squared minus 1 over 8, 0, 8. All right, so the first thing we're going to do is let's find the initial and terminal points. Okay, so when t equals 0, x is going to be equal to t, which is 0. And then y is going to be equal to 0 squared minus 1, which is negative 1. So it starts at this point, 0, negative 1. And then the terminal point, t equals 8. Well, that means that since x is equal to t, that's going to be 8. And then since y is equal to t squared minus 1, that'll be 8 squared minus 1, which is 63. So another point that we have is going to be the point 863 on the graph. Now, the next thing we're going to do is we're going to eliminate the parameter. And notice that t is equal to x. So what I'm going to do is I'm just going to substitute it back in. And we're going to get that y is equal to x squared minus 1. And we know this is just a parabola. If I can make that look like the word parabola. It's just a parabola shifted down 1 unit, concave up from the origin. So it's a parabola, it's concave up, and translate it 1 unit down. Okay. Now, of course, these are the initial and terminal points. Okay, so if I were to graph this thing, right, I would start here, and this is going to be my point. That's our point 0, negative 1. And then it's just going to go up. Okay, and let's just assume that this is the terminal point, 863. And the orientation is this way, from left to right. Okay, so orientation is left to right. Okay. So that's how we can eliminate the parameter. Okay, now this one was really easy because it was given to us already as x was equal to something in t, but it's not always that easy. So let's take a look at a few more examples that might not be as easy to work with. Okay, so a secondary example, we have x equals e to the t and y equals e to the minus t, right? And so what we can do first, and it says that t is greater than 0. Okay, so that's just the starting point. So when t equals 0, that means that x is going to be e to the 0, which is 1, and y is equal to e to the minus 0, which is also 1. So we're going to start at the point 1, 1, right? And let's just get one other point in there, all right, just so we can kind of see the orientation of this thing, all right? So if t were to be equal to, let's say something like just 1, so that means that x would be equal to e to the first, which is approximately 2.7918, and then y would be equal to e to the minus 1, and I think e to the minus 1 is, I think that's going to be 0.37 or 0.38 or something, but let me use my calculator and see. I'm hoping this has an E button on it. Okay, so it does have an E, and I'm just going to take the reciprocal. So it's 0.368. Okay, so, all right, so that way we can just get an idea. So when t is equal to 1, we're approximately at the point 279.368 approximately. Okay, and then we have this 0.11. Now, one thing to notice is that we can rewrite y as y equals e to the t to the minus 1, and then we can just substitute x back in. All right, so we can just use a little bit of sneaky algebra. Or we could just take the ln of both sides if we really wanted to, all right? But I think this way is a little bit cleaner. And so we get y equals x to the minus 1, which is 1 over x, okay? We know what 1 over x looks like, but we're also looking at when t is greater than or equal to 0. Now, it can't be equal to 0, all right, for x and y, but at least for t, it can be, okay? So here's our graph, right? So we have this, and we have this. Now remember, t is greater than 0, okay? So we're actually going to start at the point 1, 1. Right? And then from there, we know that another point, like out here, might be something like 2.79 and 0.36. So I think our graph is going to look something like this. And then the orientation is going to be this way. Now, of course, if we don't trust our answer, what we're going to do is we're just going to use foo plot, okay, to see what's going on with this. Okay, so I'm going to go back to foo plot, and remember we have x is exp of s, and we have exp of negative s, right? And notice it gives us this shape, okay? But remember, we want to go where s is greater than 0. So let's just say 0 to 10 or something like that. All right, I know it's not the exact domain that we want, but that's precisely what we got. And the orientation goes along this, okay? Remember the first one that we had that we just did? Okay, so we could verify this one as well. It was that parabolic shape and it kind of went up. So x was t, and then we had t squared minus 1. Okay, so we should always check these. So x is s, and this is s squared minus 1, and it went from 0 to 8. All right, and we'd have to scroll out pretty far. All right, but notice that the terminal point, remember that was at 8, 63 is somewhere up here. Okay, and the orientation goes from left to right, it goes up. Okay, so 2 examples of being able to eliminate the parameter. Okay, both not too bad algebraically. We get the domains of these parametrics and the constrictions on them. Okay, now we are going to look at some more examples of this. Okay, and we're going to use a little bit sneakier algebra, especially when there's trigonometry involved.